Alrighty then. The thing says we're live, so we must be live. Otherwise, that'll be weird. Hey guys, what's going on? Memes here. Now, the point of today's episode is to address a particular thing that myself and Thad have been hearing as some feedback from other folks. We presented some different things, and then we've both gotten similar responses. Something along the lines of, well, if this was to be true, that would mean the meter or the joule second would actually have to have some significance. And as we have within the doobly-doo below, it says some of the history. The meter? It was originally 1,000,000 paces from Paris to the North Pole. That was the distance. That seems very arbitrary to me. The second? It was an earthly convenience. Why? Because we can almost fit it into a standard 24-hour rotation there, give or take a few minutes. And then the kilogram was based upon a liter of water, which was interesting. And then over the years, it ended up being that hunk of uridium that was stuck in Paris that everyone's like, don't touch, or else things will get all messed up and everything. Those seem pretty damn arbitrary to me. All right. So I'm going to postulate that things that may have started off as arbitrary may not be so arbitrary. And we're going to go through and break it down why. Because again, you're like, just a chunk of metal? How could that have anything to do with nature? Okay. Now, the meter, the second, and the kilogram, those might be arbitrary units. People could argue about those, and that's totally fine. Now, when you bring up something like, I don't know, let's say the Planck length, the Planck time, the Planck mass, a lot of folks would say, those aren't arbitrary at all. Those are constants of nature themselves. But those units are also expressed in the same units. The Planck length is expressed in meters, the Planck time is expressed in seconds, and the Planck mass is expressed in kilograms. So they must be completely arbitrary, right? See, that's where things start getting interesting. Because while there might be those that say, just our base units, those are totally arbitrary. Okay, they may have started off as arbitrary, but I'm going to make the claim that they're not so arbitrary anymore. And there's a couple of reasons for that. Because, again, if you're going to say that this is a minimum length according to our knowledge, but it's expressed in meters, meters are arbitrary. So how can that be meaningful? You kind of see where some of the paradox or some of the conflict might come in, is that while we have magnitudes, I believe it was Julian Barbour that he wrote the Janus Point book, where he says that when he passes away, he wants on his tombstone just the quote, nothing but ratios. And that's ultimately what we're coming down to. It's the magnitude relationships that should hold. Now, again, I know I'm hitting on the point that, well, some folks consider our base unit, the unit we're expressing things in, whether it's meters, whether it's kilograms, whether it's seconds, those might be arbitrary. But if those are arbitrary, wouldn't that mean that our magnitudes derived from those are also arbitrary, unless they were related to something very important? Let's say, I don't know, maybe some of the constants of nature, if you would. Spoiler, that's actually what happened. So, I mean, back in, was it like 2018, 2019, CODATA and NIST, they basically redid SI in order to help make it more coherent. Why? Because I remember when they started updating things, I was looking at some of Thad's numbers and calculations, and I'm like, all right, well, this doesn't match. But the numbers that Thad had input also didn't match. I'm like, wait, what's going on here? Number one, there are also updated measurements for certain things. Number two, when you redefined SI, that kind of changed a few things, because one of the things that they did, for instance, like Planck's constant or H bar, the elementary unit of action, the interesting thing about that was it used to have 12 significant digits listed. And there was a pretty large error in the last two, so they just lopped it off and defined it at 10 significant digits. Well, because we have high confidence in that, so that makes sense. Okay, why am I saying any of this? So, first off, we've got the Gilk Man returneth. Welcome, Thomas. Oh, that's a fun photo. I like your hat. Welcome. Welcome, Poindexter. Yes. Klatu Barata Niktu. Oh my God, I remember that saying. I forget what that was from. God, I'm such a bad fan of stuff I learned in the 90s. As well, we get Tommy and the Guinea Pig Collective roaming around. Good to see y'all, and for all those who may be joining us temporally in the future, what the heck am I talking about? Okay, so I'm gonna go through, and we'll use some of the board for this. Don't worry, we won't. All you gotta know is just ratio. You're gonna have stuff related to a thing. Okay, that's one of the reasons I say the whole stuff and things, because I don't know all the stuff and things that are going on out there, but I do know that there appears to be some stuff that's doing the thing. Okay, so let's go over some basic units here. All right, so we got our unit. We're gonna go. Let's do the meter. A meter. Delicious. I always wondered. I'm like, wait, we already got yardsticks. Why the heck do we need a meter and stuff? It seemed weird. Why? Because that happens to be a unit. I'm going to put our unit up here. This is the unit. Oh, excuse me. I did that wrong already. I'm already putting out fake news. Why? This is the unit. The other thing's going to be the dimension. So this is going to be our units. And this is the dimension. What the heck is that? It's the thing that we're measuring. Okay, kind of like your speedometer. You have speedometer in your car. If it's a US-based car, you see it going like 60 miles an hour or so. Okay. Now, if you were in a car that's manufactured many other places in the world, you would see it be going at 100 kilometers per hour, because the conversion factor is like 0.6 or something like that. But ultimately, once you have a reference, ultimately I'm going to claim that these are the reference points for our units. And once you have a reference point, that in and of itself isn't enough to make it coherent. So this is going to be, the meter is a unit of length. Okay, or distance, whatever you want to think. So this is going to be the dimension. People get confused about dimension because, well, to be fair, we should probably make a few other words for that. So this is going to be the dimension of measure. This is whatever the heck we're measuring, whether it's your speed. And what is speed? It's you travel a length or distance, and then you divide it by how long it took, and that gives your speed. That's something that you don't need to be a rocket scientist to figure that out. If you've ever driven a car or been in a car, you understand that. Heck, you even understand acceleration. You ever accelerate onto the highway, it's like, oh, you start getting forced back. Why? Because you're going faster and faster and faster, and there seems to be this whole inertia thingy, yada yada. But that's not what we're going into through here. So these are dimensions of measure. These are the things that we believe, to the best of our knowledge, we are measuring. Because again, we have limited knowledge about what's going on. I realize I also should be talking over there rather than looking at the board, because I'm using my AirPods have terrible reception, so we're going through the laptop mic. So measure. All right, so we got our dimensions of measure here, and then what else do we got? We got the meter. Well, we're talking about distance. We're talking about speeds. We need time. So we got our unit, which is the second. Let me get a new marker. This one is kind of bleeding out. There we go. It's good. Yes, dark marker. Okay, and the second is a unit. Time. Time. All right. You get these things. You get a length divided by time. That's a speed. That's what you'll sometimes hear as a derived unit, or sometimes people will say it's a derivative of this. And you hear derivative, and I still get scared. What's that mean? It's you're showing a relationship between other things. I could be wrong, and again, I'm sure some mathematicians will have my head, but for the sake of this discussion, we're just going to go over this really quick. So then we were talking about the kilogram. Why? It's a gram. That's about the mass of a large paperclip. At least that's what they told us in elementary school. So, kilogram. Okay, well, that's a unit of mass. And one of the things that confused me when I was in high school and stuff, it's like, oh, we usually express things in weight. The net weight of this. And you can use those things and everything, but ultimately, if you're in space, you don't really have a lot of gravity affecting you, you're probably not going to weigh that much. So your effective weight is kind of zilch. Yeah, probably a little bit, but not too much. Now, your mass is going to stay the same. That's the thing. Now, if you happen to be on, I don't know, let's say hypothetically we're standing on like a neutron star or something, and you manage to not get incinerated because you're using a suit of unobtainium or something, okay? You stand on that neutron star, now you may weigh like, I don't know, 200 pounds, 100 kilograms, whatever it is on Earth. Your weight is going to be a heck of a lot higher because the gravitational force of that neutron star is like magnitudes. You're probably going to be a pancake before you get torn apart and stuff. Okay. Your mass, however, will remain the same. That's like the big difference there. All right. That's a unit of mass. Okay. We're going to go over these three guys real quick because these are the core important ones. So you also see, CGS, like centimeters, grams, and seconds. And they'll relate that, and that's another system. And the whole point of this, hey Rick, good to see you. I just posted a little bit of a clip of some of our discussion from the other week there. The law of exponents. Rick is saying that ratios are special cases of integer powers. Ooh. Oh, that sounds useful. Yes. Oh, Evil Dead in the Army of Darkness. Okay, I get it. Thanks, Tommy. All right, because I was going to say Klaatu Barata Niktu. I don't have the Necronomicon around. I do have a new kind of science that I opened up earlier, so hopefully that's not going to initiate some hidden code that Wolfram put in there long ago or something. Okay. So let's just go into some of the history. Why? Because we're here and we have the internet. So here we go. This guy. All right. Let's go into some of the history of SI. All right. So SI, aka the International System of Units. Oh yeah, SI, because that's just what we call it. Okay. So let's do it real quick. Over here. The International System of Units, internationally known by the abbreviation SI, is the modern form of the metric system and the world's most widely used system of measurement. It is the only system of measurement with official status in nearly every country in the world, employed in science, technology, industry, and everyday commerce. The SI system is coordinated by the International Bureau of Weights and Measures, which is abbreviated BIPM. So that's from the French there. All right. So here's the big thing. You can say these things are arbitrary. That's fair. Until you utilize them in a coherent fashion. AKA, once you reference things, AKA, if you're going to measure some power output for something or whatever you are measuring there should be coherence. And that's why I call this stream what it was, the unreasonable effectiveness of SI. Why? Because you hear the term the unreasonable effectiveness of mathematics. Why the heck is it that we can use math to actually describe the world? Did it need to be that way? Maybe it did. I don't know. But it's very interesting, so I'm going to claim the unreasonable effectiveness of SI. Number one, I am very biased. I would totally want this to be true. Now, it's taken me a long dang time because even when I went on to shout out to Shoutout and Anastasia for their episode of Paradigm Drift last week and everything, what was it? That's ultimately one of the questions, getting like some of that feedback and everything there. It's like I realized I was presenting something, but I didn't really have my story or my point there because, basically what I was presenting, I could have figured it out probably like a year or so ago. I'm like, oh, what would I need to make this work? I'm like, I could just plug in arbitrary units. I'm like, plug in the meter or the joule? I have no justification for that at all. I mean, what's my justification? Number one, when you plug it in, it's this very suspicious agreement with a lot of the measurements there when all you have to do is literally add a dimensionless factor of pi divided by 3. I'm like, oh, a circle divided by 3. It's kind of, according to Thad, he's like, oh, that's kind of a representation of a pseudosphere. Pseudosphere? I don't know. Isn't there something within general relativity, pseudo-Riemannian manifolds? I don't know. But the interesting thing is once you have a coherent system, aka everything's going to reference everything, and everything should fit together in a way that works. Think of it kind of like a Rubik's Cube. Yeah, it might be all messy and everything, but if you do the correct articulation of things, you're going to get your red side, your blue side, your yellow side. I forgot the other colors there. But this is one of the things. And ultimately, even if before you didn't really believe in it, this is now actually tuned to the constants of nature. Okay. So let's go through this real quick. The SI comprises a coherent systems of units of measurement, starting with 7 base units, which are the second, the meter, the kilogram, the ampere, the Kelvin, the mole. Yes, not your fuzzy ones there, but the Avogadro's number of particles. The amount of stuff, the candela, the measurement of luminous intensity, which I may have some issues with it, but okay, regardless. The system can accommodate coherent units for an unlimited number of additional quantities. These are called coherent derived units, so basically kind of like speed. Because if you're in your car, you're driving along, and you go 60 kilometers in 1 hour, or 60 miles. All right, you're going 60 miles an hour there. And the problem with miles is you could use that, but you're going to need to set references and then have everything else cohere. That's why SI is one of the useful things, because it seems to be very coherent. Okay. AKA, if you have a length divided by a time, you get speed. That's a derived unit. Okay. AKA, the speed of light. If you take a minimum length and then you divide it by a minimum time, you're going to get the speed of light, approximately. There may be some caveats there, but just general first level analysis, yes. Okay. So we have all these things, blah, blah, blah. So let's go into, okay, so basically, what is it? We got speed, let's see, what are we? So time is basically based upon the frequency of the radiation of cesium-133. All right, so what's that? That's about 10 billion oscillations per second. Okay. The speed of light. Oh, look. Yeah, about 300 million meters per second there. All right, so Planck's constant, the joule second, elementary charge of the electron or a proton, Boltzmann's constant, Avogadro, luminous efficiency of, yes. Okay, now let's actually go into some of the history here. So let's do this. So let's do SI meter history. Well, this should be fun, because it's a national system of units. Hey, welcome, Kali. Good to see you, my friend. Well, I mean, maximum minimum connecting, I'm very biased. I personally, I think so. Now, what that may mean for us, that's an interesting question. We're not there for right now. The water ratio. Well, here's the thing. I think there was a point, Rick would know this better than I would, is that initially it's like a kilogram was defined as a liter of water. Coincidentally, if you take 1 cubic meter of water, it comes out to suspiciously really dang close to 1,000 kilograms, which is very useful. And I think, what is it? If you add a cubic meter of water, you need to add in something like a little bit of a pinch of salt, and you're literally going to have, it can be with the appropriate solution, precisely 1,000 kilograms, which is an interesting thing. Rick has pointed that out, and hey, I mean, we used it for a while, so it must have been useful. We continue. Well, I'm not going to make that claim, but there are certain things that get the old noggin a jogging, Poindexter. Hey, Six! What's going on, man? Well, right now, let's see, where are we? I happen to be in the Physics Monastery right now, and somehow I became a physics monk talking about scientific stuff and things on the internet. That's where we're at. So now we're discussing SI and basically the metric system and its unreasonable effectiveness. So what am I talking about here? Okay, so let's go back here. And let's go to... Oh, wait, no, I clicked on the same dang thing. Let's go to the history of the meter. There we go. All right. So the whole thing initially was... All right, so they defined it as the distance from Paris to the North Pole, assuming early measurements of the distance. So they're assuming Earth flattening, blah, blah, blah. So they defined it as the distance there as 10,000 kilometers, I believe. Okay. So as you can see, yep, that's a little thing. All right, so distance from Paris to there. Oh, excuse me. I was totally wrong. It was supposed to be from the North Pole to the equator. All right. See, look, I'm already putting out fake science and stuff like that. God. Okay, I was going to say I'm like 10,000 kilometers from Paris seems... On its face, I should have realized that's wrong. All right, I'm going to have to make a correction. But the picture is correct there. So basically, you're going through Paris from there. It's approximately 10,000 kilometers. So that's what it was originally defined as. Okay. So let's go to the second. The second itself, well, I think we all know what that was. We got about 24 hours in a day, but about 60 seconds in a minute, 60 minutes in an hour, 24 hours. It's an earthly convenience. Can't be important. Let's go to the kilogram. The kilogram is going to tell us basically, yeah, they talk about the iridium and stuff like that there, but let's go to kilogram. So, but it was originally, I believe it was 1795, something like, yeah, 1795 during the French Revolution. It's defined as the mass of 1 liter in water. The current definition of a kilogram agrees with this definition to within 30 parts per million. That's pretty good. That's pretty dang good. And then in 1889, they replaced it with that cylinder. You see it's protected there, and then they need a copy so everybody could have a reference unit and stuff. But ultimately, that's what we're talking about. These are the reference ones of the system. Okay. So what am I talking about? The meter is the reference one of length. The second is our reference one of time. The kilogram is our reference one of mass within this particular system here. So, hey Jax, good to see you, my friend. What's going on, my dude? Good to see you. Yeah, well, cubic feet and pounds. Well, this is the thing. You're going to need to set the entire system to be a reference. That's why random side quest story. So when I was more in my political sphere of things, I went to a town hall meeting for a particular candidate, doesn't matter who. But I was at that meeting, and somebody asked that candidate there. It was the first question, and it kind of blew my mind because I had never considered it. They asked, will you take us out of the dark ages and make it so that the United States adopts the metric system? And it's like, he gave a really impassioned, powerful speech, and I'm like, I had never considered it. The candidate had never considered it, and we're all kind of like, well, that's not what anybody was really thinking of, but that dude was. Shout out to that dude. I have no idea who he was, but he brought that up, and yeah, you spent some time doing some calculations and stuff, and you're like, yep, that makes things a lot easier. And then you also have Wolfram Alpha, just putting the stuff and does most of the stuff for you, but I digress. So the claim is these are our references from the system, because even if you think these are arbitrary, we're going to go to our constant. We got our units, and we've got our constant. So even if you think these are totally arbitrary, if you're within physics, you're going to not view these as arbitrary. So the constant of the meter, it's a unit of length, so we have our Planck unit, so it's Planck length. Our unit of time is the second, so, well, duh, it's going to be another Planck second. And then we got our kilogram, it's a unit of mass, so, oh, I know, we got a three-peat here. It's the Planck mass. Okay, so the claim is that even if you believe all these are just completely arbitrary, the magnitude relationship between these units that may have started as arbitrary, that we refined over the years and are now literally tuned to the constants of nature, even if you believe those are arbitrary, these units over here, if you happen to be within physics, I'm pretty sure most folks are going to say they're not arbitrary. Why? Because it's some derived relationship, like the second is like the square root of the speed of light to the fifth divided by the Newtonian gravitational constant in h bar. Maybe h bar is squared. I think it's squared there. Maybe it's not. See, reference the video I did with Rick last week or so ago. It's all there. But here's the thing. Once you have these things, it's like, all right, the meter and the second, you go 1 meter per second, who cares? But if you take the Planck length, so if you take your Planck length and you divide it by the Planck time, you're basically going to get the speed of light. Speed of light, aka small c. Cool. Now you might think the meter and the second are completely arbitrary. That's totally fine. Speed of light, if you're within, let me go over here. If you're within the physics or scientific realm, I don't think people are going to assume the speed of light is arbitrary. Now a lot of folks would want it to be that 300 million meters per second, and to be fair to an approximation, it kind of was, or it is very close. Actually, there was a good period of time where we had 0 significant digits of the speed of light. AKA, we thought it was 3 rather than 2.99, yada, yada, yada. It's mind jab. But here's the thing. Okay, now, if the speed of light is not arbitrary, and the Planck length and Planck time, therefore, are not arbitrary, does that mean that the meter and the second are not arbitrary? Okay. The coherence is the thing. And now what I'm talking about is these are our reference ones. Now, whatever they may have been, at this point, the meter is tuned to the speed of light, the second is tuned to the frequency of cesium-133, and the kilogram is tuned to the elementary unit of action, h bar, or Planck's constant. Those relationships don't seem to be quite as arbitrary, because these are our reference ones of the system. Why? Let's have a quick little demonstration. Let's go over here, go to our friend. Wolfram Alpha, boom, okay. Go this guy. All right. So let's just do the speed of light. Boom. Speed of light. C. Get to all those digits. All right, so we got all 9 digits of the speed of light right there. Okay. So let's say, let's do, what we divided by? Let's divide it by, we divided by the Planck length. Oh, we got this. Oh, that's the Planck frequency. So technically, let's just do it this way. Boom. Oh, the Planck length divided by the speed of light. Oh, look. It seems to be the Planck time. Okay. Now, none of this should be surprising at all. What should be surprising is this. Is when you take the speed of light, you divide by the meter. Oh. So we got that unit out. So now we just have a unit of time, and that's in the denominator, which the inverse of time is frequency. Oh, well, that's interesting. So we could also do this. Meter. Okay, so we're getting an inverse there. So notice these digits, 3.336 times 10 to the negative 9. Okay, don't worry about the dimensions. What happens if I put a 1 above it? Oh, 3.336 times 10 to the minus 9. Now it's a different dimension. It's the same magnitude. See, that's the thing, because if you divide the speed of light by meters, divide by seconds, oh look, we're getting the same digits as the speed of light. That's very interesting. Why? Because these are our reference ones of the system. Okay. So let's go to something a little less arbitrary. This is one of the things, it took me a while, and I'm still trying to grok this. The thing that got me was when I was working on some other things, and you do something like the unit of the joule. What the heck is the joule? Let's actually figure out what the joule was. It's SI joule history. All right, we got the joule here. The joule, symbol, big J, is the unit of energy in the SI. In terms of SI-based units, 1 joule corresponds to 1 kilogram meter squared per second squared. Okay, so 1 joule is 1 kilogram times meters squared divided by seconds. Okay, it's the amount of work done for the force of 1 Newton to displace a body. Okay, so let's try this because we have our thingy there. So 1 joule equals, all right, let's do it out. 1 kilogram meters squared. Let's divide by seconds squared. Wow, that's very neat. To be fair, I feel like, did I know this? I may have not even connected these particular neurons. But the interesting thing is, this is on Wikipedia. Okay, so you look at that, that's cool. But maybe this should be a clue. Meter squared, and then since it's -2 there, that's just meter squared divided by seconds. Oh, wait a second. Wait a second. Let me just do this here. M squared, so meter squared, S squared. Wait a second. If a meter is a length, and then we're dividing it by a time, wait a second. So a length divided by a time is speed. And if this is all squared, this equals speed squared. Now, oh, sorry. So if we have speed squared, is there something we know about a particular speed and something interesting happens when we square it? Well, seeing as we already have it on the board, we already have the speed of light over there. That's a length divided by a time. So if we swap this out to let's just do the notation for L sub P, the Planck length squared, over T sub P times squared. Well, this all just equals C squared if we used it by those units. Okay, again, I haven't proven a point here. I'm just saying words. So we did this little calculation, and it seems to come out right. Okay. Now, if this is a coherent system, let's say, I don't know, this gives us 1 joule. Let's click on 1 joule. Okay. So a joule is, we got our units here because Wolfram takes care of all that stuff for you. It's a mass. So we got a mass and a length in time squared. Wait a second. Length in time squared. Let's do something. Let's just try this. Just because we can. Let's divide it by c squared, the speed of light squared. What do we get? Okay. We get this. All you need to know, we got some digits and a very small number. Okay. It's expressed in a dimension of kilograms too, a dimension of mass. 1.113 times 10 to the minus 17. Now, we have that. Now, the interesting thing is, what if we did 1 over c squared? Okay. Wait a second, these digits look familiar. 1.113 times 10 to the minus 17. Now, the dimensions of measure are different. Wait a second. 1 over c squared, 1.113, 10 to the minus 17. 1.113 times 10 to the minus 17. Now again, I understand that, this is expressed in this, but isn't it kind of interesting that we can divide by the mass energy conversion factor and we get the same as if we treated this as 1. Now again, the dimensions are different. The magnitude relationship is the same. Why? The reason why I claim is the joule is the reference 1 of energy. That's basically the argument for that. Now, where do the others come in? That's a good question. We're going to connect that, but since, let me go through the chat. Yes, let me see. Blank time, not second. What did I do? Oh, okay. Yeah. I think I see. That's the only problem with the internet. You got to check time, blank time, takes Planck frequency, gets the second. Yeah. Planck time times the Planck frequency gets the second. C is derived from, was it 1 over square root of, oh God. Sorry, I'm used to going to the brackets. I've been working on trying to learn the code. Electric constant. And magnetic constant. So that should be, yep, okay. Yep, speed of light, 2.99 times 10 to the 8 meters per second. Yep. I remember when I was first playing around Wolfram Alpha, I'm going through and I'm like, oh my God, I discovered what Maxwell did like 150 something years ago. Wow, the speed of light is 1 over the square root of electric constant times a magnetic constant. Yes. Okay. Now here's the thing. I'm going to show, hold on, let me finish going through this. Let's see, what else do we got here? Okay, so Jax, there's an interesting thing I learned from Professor Norman Wildberger. He's a mathematician down in, I believe, New Zealand. He has a quote, and the quote is, repetition renders the ridiculous reasonable. If you say something enough times, if a bunch of people start saying it, oh, that's just what we do. This is just how we talk about things. And then people might not even know why they're saying things. So there's some memetics in there, but it's not the topic for this video. Hey, Snacks, what's going on, my dude? How are we doing, my friend? We need to get back together when we go back out to the East Coast. But okay, I'm getting to the point. Don't worry, Six. So there's an interesting thing. I think I mentioned it a little bit the other day, but I had a little conversation with ChatGPT asking something about units and metrology. So basically the study of measurements and stuff like that. Long story short, it ended up saying something along the lines of, while it is generally assumed that all physicists have a knowledge of units and all this jazz and everything, there happens to be a surprising lack of literature on dimensional units, as well as basically there seems to be a lack of literature on the topic. If it was an important thing, you would think there would be more literature. So again, I'm not saying that people just miss something. I'm just saying that, listen, we've done a lot of work. We've done a lot of measurements over the years. Literally, to get to the point we're at is literally the sum total of human knowledge over millennia. We've done pretty dang good. Personally, I think we can do better. But that's the whole point of leveling up. So let's actually get to what I'm talking about. Okay. So let's say we have, I'm going to show one quick example. Okay. The whole point is to have a coherent system of units. So basically, if you're going to have different units and you're going to have these magnitude relationships. So if we've got length, okay. They're going to be coherent. We believe they're going to give us the speed of light, okay, to at least a large amount of digits. Okay. So what happens if we change this? Well, let's just say, we're gonna change the meter. Okay. Now, you change the meter, so it's going to be half of what it was. Okay. Well, the thing is, if you change the meter, you're going to have to change the Planck length. So if you're going to decrease its magnitude, the Planck length would by necessity go down as well, because you're going to have a reference there. Those words because basically if you have the Planck length, that's not the speed of light. Basically, if you're going to adjust any of these base units, you're going to have to adjust so the system is coherent all the way through, especially once you're tuned to the speed of light. So as you can see here, well, if the Planck length was less, so let's actually just do it to the reference itself. So the meter, let's just do this. Meter divided by a Planck length. Let's do it the other way. Because the meter is a 1, we're essentially dividing by 1. Okay. So it's giving you this number right here. Very, very small number. Okay. So what if the meter was 1/2? Well, the meter was 1/2. Well, that's not going to be the magnitude of the Planck length anymore. So we're going to have to adjust this as well. Okay, so that gives us the ratio magnitude. Gives us that magnitude, but the Planck length was half of what it was. That means it would be smaller, aka once you set your references and you get the magnitude relationships within a coherent system of measure, your ratios should be telling you something. So that's ultimately the claim. So basically, if you were to divide the meter in half and make it smaller, well, the Planck length by ratio would need to effectively be smaller, because now you've redefined what the meter is. Once you set up the definitions, they may be somewhat arbitrary points, but once they get tuned to the constants of nature, they're a little less arbitrary. Now, I've been saying the word coherent and everything because, somebody was talking about, it was actually a fruitful discussion. Like it was one of the people that I follow and happens to follow me, they were talking about basically, what was it? Trying to think what they said. Oh, they were saying what was it? If you're taking like these roots and everything, it's like, well, if you were to do this, it was basically about that calculation, the claimed way to calculate the Higgs boson mass. And they were saying it's like, oh, you're going through, and I'm like, well, if you use a coherent system of units, and at one point it was like, basically they were saying is that the joule was h bar is like 10 to the minus 34, yada yada. Okay, well, if you did that value in electron volts, it's not going to work. I'm like, well, I did the calculation with electron volts, and since SI is coherent, it came out to be of the same magnitude. And at one point I'm like, well, I did the calculation. It does come out because the coherent system of units. And then you heard, it's like, well, if you use a coherent system of units, yeah. It's like, well, why wouldn't we use a coherent system of units? Isn't that the point? I just don't think that this has necessarily been thought about as the meter. It's just an arbitrary distance, or like the North Pole to the equator. Who cares? Yes, see, I got it right that time. And then the second is an earthly convenience, and then the kilogram, it's like a liter of water and stuff. So, what if we were to postulate the claim? Once we set a coherent system of units, that we can reference them, and Rick was talking about basically if you have the Planck time and then the Planck frequency, well, that's going to give you a second. Why? Because, well, the frequency is inverse of time. It's what happens when you do 1 over time. So if you have a thing and 1 over a thing, guess what? It's going to cancel out to 1. That's very neat. Okay. I understand this probably isn't satisfactory enough. Let's make this more satisfactory. And this was one of the initial things that really got me into the whole like Physics Monastery, and really was impactful that I had learned from Thad. Now, you may have heard from different folks. I think I had first heard it from Professor Sean Carroll. Was that once you have F equals ma, so force equals mass times acceleration, you can basically generate all of physics. What the heck does that even mean? Okay, so let's bring up this guy. So bring back here, share with class. Okay, so let's go to this guy. Okay, so let's go over to coherent. Coherence, units of measurement. There we go. There we go. All right. So yes. If you've made it this far through, here's where the payoff is. All right. So a coherent system of units as a system of units of measurement used to express physical quantities that are defined in such way that the equations relating to numerical values expressed in the units of the system have exactly the same form, including numerical factors as the corresponding equations directly relating the qualities. It is a system in which every quantity has a unique unit or one that does not use conversion factors. Okay. At least the question, what are conversion factors? Conversions of units, okay. Conversion of units is the conversion of the unit of measurement in which a quantity is expressed, typically through a multiplicative, aka you probably like multiply or divide something, conversion factor that changes the unit without changing the quantity, okay. This is often loosely taken to include replacement of a quantity with a corresponding quantity that describes the same physical property. Okay. Unit conversion is often easier within a metric system, such as SI, than others due to the system's coherence and its metric prefixes that act as a power of 10 multiplier. Oh, that makes things a lot easier. If we could have base 10 or something like that, God, that would make our lives a lot easier. Wouldn't that be neat? We go back to coherence. Okay. And then we have over here, we'll just touch this, a derived unit, that for which a given system of quantities and for a chosen set of base units is the product of powers of base units with a proportionality factor being 1, aka length divided by time is speed. If it happens to be Planck length divided by Planck time, we're pretty much going to get C. Okay. All right. So those are words. That's Wikipedia. Don't necessarily believe this. Feel free to trust if you want, but please, good God, verify. All right. Here's the thing. Dimension-related coherence. Okay, those are a bunch of words. This is what really got me into this conversation is when Kevin was out here and Thad had posted that video. Okay, so here we go. Let me hydrate a bit. All right. Each variant of the metric system has a degree of coherence, the various derived units being directly related to the base units without the need of intermediate conversion factors. An additional criterion is that, for example, in a coherent system, the units of force, energy, and power be chosen so that the equations force F equals mass M times acceleration A, and energy big E equals force big F times distance little d, as well as power big B equals energy big E divided by time small t. Hold without the introduction of constant factors. Once a set of coherent units has been defined, other relationships in physics that use those units will automatically be true. Einstein's mass-energy equation, E equals mc squared, does not require extraneous constants when expressed in coherent units. Oh, that's very interesting. Huh. So let's go through that, and then we can start to wrap up. Okay. So what do we have here? Let's go back. So force equals mass times acceleration. So let's do this. So force equals, let's just use Planck units. Planck mass, and then acceleration is length divided by time squared. So let's just do this. So then we're just going to do this. Planck length divided by Planck time squared. Throw this back in here. Okay. So what we got? We've got, finish putting our mass term in it. All right. So we've got mass, and this should be acceleration. If I take the extra bracket out. Okay. So this is force. All right. So we got the Planck force there. So that's a unit of force. Okay. So the other thing that we need is we need energy. So that's force times distance. So if distance, that means we need a length. So that means we take this guy out. We'll throw some protective brackets over there. Now we're going to multiply it by distance. Okay. So for those of you that might be more physically inclined, you may notice we've got a mass and we've got a length divided by time squared. If we add another time in there, we've got, oh wait, that ends up being c squared. Oh, so force times distance equals energy. Oh, looky, Planck energy. We're in the right dimensions. So what was the last thing we needed? We need power. God, the memes still live within home improvement. Power. So that's just energy, what we got there. And then we divide out a unit of time. Okay. So if we've got all this, so let's see if we can get an intuition for what's going to go on here. Because it took me a dang long time because I don't have a formal physics training background. Okay. So we've got energy. So if we're going to divide by time, that means time goes into the denominator. So right now we have two of them in the denominator because that's negative. So that means it goes down below. So if we're going to divide out, that means it's going to go to time to the -3 because we're going to have 3 in there. So that should give us power. So let's do it. Let's divide by the Planck time. Let's see what we got. Oh, look, we got the Planck power. Yep, we're in the dimensions of power. So the whole point of this is once you have a coherent system of units, and they can reference each other, and you can go back and forth. Basically, once you get F equals ma, that force equals mass times acceleration, if you have coherent units, you should be able to multiply that force times distance to get energy, as well as take that energy and then divide it by time to get power. And at this point, you now have a coherent system of units. Huh. That's very interesting. Why? Because what it might mean, and again, I could completely be barking up the wrong tree. I could be just the most wrong dude in the world. But the interesting thing is, once we set these reference points, these are our ones of these dimensions. So we can effectively treat them as ones. That was basically the whole hack that I did, where it's like, oh, to get this work, it's like, well, I just do joules squared, energy squared, divided by the Planck energy, throw meters cubed in there. So what do we got? We got the reference energy, reference one of energy squared, divided by the maximum one of energy, as well as the reference one of volume. And then a pi divided by 3 term, and that happens to fit the vacuum energy density, at least according to the more mainstream previous measurements, really dang well. You want to be open and transparent, and there are ways to account for some of the other stuff. But it's just very interesting that the thing that blew my mind was, as soon as I divide I didn't know a joule was tuned to c squared. Does the Wikipedia article even have that? Let's go back. Joule. Let's see. Because I looked before and I didn't. I mean, you got speed squared there, but it's tuned to the kilogram. Okay. 10 to the 7 ergs. We like our powers of 10 to the 7 and minus 7. That might be very useful. The definition. I don't see it saying c squared anywhere. I mean, I just could be wrong. Maybe that's just assumed. I think I asked Dad. He's like, they didn't teach us that in school at all. Because that was the thing. The only reason I knew was because of Wolfram Alpha. Because, what was the calculation? It was, I think I did joule equals, oh no, what did I do? I think I did this. I tried to do the geometric mean square root of Planck mass times the Higgs mass. I think this is what we did. So right now, what we have 2 units of mass. We're multiplying together. So if you multiply a unit by the same unit, you get the unit squared. But we're taking the square root of that, so we'll be in a single dimension. So this is also called taking the geometric mean of something. I totally learned that after. I was just doing the thingy because it worked. Or it seemed to give you some things. Okay. So this is the thing that caught my attention. Because at first I had just done that random little hack. It's like, oh, this seems to have got agreement with the Higgs boson measurement. I got to find a way to justify this. So I had done the whole, where is it? The Higgs mass divided by the Planck mass. Okay, gives you this number here. I'm like, all right, well, that's interesting. So I divided. What if we multiply? Well, let's just multiply. We're gonna get. I was trying to do a conversion there. Let's actually. Let's do multiply. Yep. Oh. Boom. Okay. So you get this thing. I can't make sense of that. So we take the square root. Okay. So all I know is I'm looking through this, blah, blah, blah. I'm like, okay, that's cool. Doesn't really mean a dang thing to me. Wait a second. 6.3, that's kind of close to 2 pi, because 2 pi is like 6.28-ish. So I'm like, oh my God, is 2 pi the relevant mass of 1 joule? What the hell is one relativistic mass of 1 joule? So relativity, okay. So, oh, that's c squared thingy. So if we do that was the thing that got me onto the joule. So I'm relativistic mass of 1 joule. So I'm like, all right. So 1 joule divided by c squared. That was like a 10 to the minus 17 number there. Oh, look, 10 to the minus 17. Oh, that's very neat. Which also happens to be the whole, since this is the 1 of energy, we get 1 over speed squared. Oh, look, it's got the same magnitude. Why? Why the heck does any of this work? I'm going to claim it's the unreasonable effectiveness of SI. That's what I got there. And again, a lot of this, I apologize, it was a bit of practice for me because I've never actually made this argument. And one of the things, again, from the whole paradigm drift, I'm realizing, I'm like, all right, number one, gauge your audience. Because if you're supposed to be doing it, the generalized elevator pitch that your average Sally, Dick, or Jane can understand, if you start coming on, you're like, oh, energy this, blah, blah, blah. It's going to confuse some people. It's like, listen, we got some stuff here. It's doing some things. We're going to go over the stuff doing the things and basically just look at the relationships there. So the whole ploy of this right here is to basically just make the case that these are reference ones of our coherent system. Because once the system coheres, now you have a framework you can actually use to figure out what's going on. I mean, otherwise I don't think a lot of our modern physics and stuff would work. Again, I could just be blowing hot air. I already had the original definition of the meter wrong. I was saying it was the distance between Paris and the North Pole. I'm like, yeah, 10,000 kilometers. Yeah, it's more like the distance from the North Pole to the equator by root of Paris. Why? I don't know. Maybe somebody actually measured it or something, or tried to. Estimation. But yeah, that's basically what we got. Let's go back through. We got some other stuff here. Let's see what some folks are saying. Oh yeah. No, it is a strange world, Jax. To be fair, Poindexter, the shut up and calculate. I love conversating. When I did actually make potentially meaningful, I don't know, discovery. Is it really? When I found the most interesting things, I just sat down. I just put on some music and I just went through the calculations. I did the work. So to be fair, I'm kind of a bad example. I don't necessarily agree with the shut up and calculate. I think questions are useful, but occasionally maybe it doesn't hurt to stop talking and do some calculations. That's all right. Let's see. Oh, that's fine. I wasn't a great reader and stuff. I needed to be interested in different things for me to get into whatever I'm doing. It's the elegance. It's I know somebody was talking about or some design or fine tuning. It's like, I can't say that. Does my mind go there? Sure, but you got to follow the evidence, and that's ultimately the big thing. It's you follow the evidence. If these are our reference ones of a system, even if you think they were originally totally arbitrary, they are now tuned to the constants of nature. And if you didn't believe that these guys are arbitrary, those guys are not arbitrary, or at least according to most any physicists we could do. So, but hey, what's happening, Charlie? Good to see you, my friend. We're just wrapping up. I did also post a video with Rick, who is here right now. Did a little clip from our discussion about the power of exponents. Oh, no, thanks, Rick. I always love to level up, so it's kind of the whole. I actually need to order new shirts. Because something about a 17-year-old shirt that's already falling apart, it's got its use. So I'll do like the standard pretend superhero thing and order like 7 of them. So yeah, that's about all we got right now. So thank you all for letting me practice with all of you, trying to help refine some arguments. And Any comments, hey, feel free to leave in the chat, the doobly-doo below, and we'll talk again tomorrow. So other than that, take care of yourselves. It's a crazy world out there, and peace out.